Can everyone see the screen? Um, all right, yeah, thanks for the introduction. Yeah, so I'll kind of get into the meat of the seminar and talk about, again, how we do inverse design in Tidy3D, what sets us apart, and in my opinion, why how we've built this ideal inverse design tool. And I have to say, just looking back, it's been 10 years since I've gotten into this business, and just kind of, I feel like this is the culmination of a lot of work, and not only the simulations, but also software and hardware, and it's really exciting to be able to kind of show it off today. So let me just first address maybe some expectations you might have when you hear about inverse design, especially if you're kind of unfamiliar with it, and just sort of address those right away. So you might kind of have this idea that inverse design first is very complicated, like there's a lot of mathematics involved, there's a lot of these algorithms involved, and it might be kind of hard to set up and do. The other thing people think of when they think of inverse design is, these kind of crazy looking structures. You might think this is a bit uncontrolled. I get some unintuitive device that's maybe difficult to fabricate. And the last thing is that, when you see papers in inverse design, they're often done in 2D, somewhat small devices. So you might think it's slow and kind of limited in its kind of power and flexibility for, handling large scale problems. So what I hope to convince you today is that these 3 points are kind of the opposite. So with Tidy3D, we've really finally built a tool that can kind of flip all of these on their head. So the first thing is that I'll show it's very easy to do inverse design with Tidy3D, even if you have no background in inverse design and very limited FDTD background. I'll also show that because of the flexibility of the way we've designed everything, you have ultimate control over how you set up your inverse design. So you can do a lot more than just these kind of cookie cutter problems. You can do very targeted inverse design, even with parameters that you care about in your system. And finally, as was mentioned a lot, because this is all backed by our massively parallel GPU solver, these simulations and inverse design optimizations are done extremely quickly. So as I'll show, we can do large scale 3-dimensional inverse design problems in under an hour easily. And these kind of problems would take days to solve on a regular CPU-based FDTD. So that really helps with making this a practical benefit in the community. So here's the agenda of my talk, be about 30 minutes. First, I want to go through a quick example and just show you how easy it is to do inverse design in Tidy3D. Next, I want to show you that there are multiple ways to do inverse design, and using our functional interface, you can basically do just about anything that you would like to do with inverse design. So that will be kind of the main subject of the talk. So I'll talk about how we can have this flexibility. And the way we do it, which was kind of alluded to, is through what's known as differentiable simulations. So all Tidy3D simulations are kind of automatically differentiable. And I'll talk about how that's done, what that gains you, and how that plugs into kind of the whole machine learning and optimization ecosystem in Python. And finally, I'll show a few examples, just selected examples to kind of inspire you to show you what kind of problems you can do with Tidy3D. And hopefully that gets you interested in trying them yourself. So first, I want to just kind of hopefully show you how easy it is to set up an inverse design problem, run it, especially if you're coming from very little experience with it. So we're going to take a waveguide bend problem as an example. So we can, we're going to basically set up a topology optimization of a waveguide bend. So we can set this problem up. We can set up just the starting simulation, either using our graphical user interface or using our Python interface. I'll kind of stick with Python for now, but we'll talk about the graphical user interface later. So the problem setup is as follows. We have a waveguide on the left with a modal source, and then we have a waveguide coming out the bottom, and we're going to be measuring the power in the fundamental mode coming out of this bottom. And in the middle, we have this coupling region, and this is what we're going to want to design. And our objective will be to maximize the coupling from the source to the monitor. And just for good measure, we're going to be doing this problem in 3 dimensions so that it's a bit more computationally expensive. So you can set up this problem in your, with regular Tidy3D components by, specifying these geometries, materials, sources, monitors, boundary conditions, etc. And now what I want to talk about is let's say you've set up your simulation. I just want to show you how easy it is to turn this simulation into now an optimized device. Of course, if you start with this device here, you will get something that performs really poorly. So what do we need to add to get this thing to couple to the output waveguide? Now, we have one interface for defining these inverse design problems, which are basically done by adding certain Python data classes to your simulation to specify various things. So for example, I can specify a mode power that just picks out the power in this waveguide. It's just a simple Python class. I can specify some object that tells me how to discretize my design region and the boundary, the bounds of the permittivity within there, which will give me, in this case, 90,000 parameters. And then there are various classes that I can customize to introduce some penalty that makes sure that I have a tunable feature size, so I can specify how large I want my feature size. And if it gets anything smaller than that, it will start to penalize the objective. So that helps us create fabricable structures. So these are all defined in a kind of high-level interface. And then to set up the entire inverse design problem, you just need to kind of combine all of these classes together. So this is the entire code in the actual example. And there's a notebook on our website. You can run this example later if you want. So this is all the code needed. So you set up the design region and the various penalties and transformations you want to do on the parameters. Define your objective function. Combine everything together with your base simulation. And then just create an optimizer and run the optimizer. And if you run this in about half an hour, again, with a 3D problem, it only takes about half an hour to get a final device. So here's an animation of the kind of parameters. And you can see the final device we get is doing a great job at coupling. Now, let's talk about the speed of this, just for reference. So this took 35 minutes. And again, this is a 3D problem. There were 25 iterations in this case of the optimization. So each iteration was a minute and a half. And every iteration takes 2 simulations, which is about 45 seconds per iteration, including the upload and download. If you were to run the same problem on a CPU-based FDTD, this would easily take over a day to complete. And it's not even a large problem in terms of area. So that's showing you how simple it is to do in Python, and that has already been available for some time. But we're also releasing in just a few weeks a graphical user interface version of this to make it even easier. So it kind of follows the same process as I just explained, but I'll just give a quick 1 minute long demo just to show you what that looks like. So we have this graphical user interface, which alternative to Python, if you are more comfortable with that for setting up simulations. So first I'm going to load in the simulation and run it. So this is just the starting simulation. And you can see I'm running the simulation and I can just visualize the results to see what I'm starting with here. So you can analyze the field patterns and the intensity patterns, and you can verify that it's not coupling very well. So what you do next is you can basically convert this simulation now to a topology optimization problem in the GUI. When you do that, what you do next is you just have to specify your design region, so the pixel size and various parameters. You specify your metrics. So for example, your output power, and you can specify combinations of various metrics with different expressions. And finally, you need to set the optimizer. So you just tell it how many iterations, the learning rate, and various other parameters. Now we can set up the inverse design problem. We can validate it and estimate the cost before we run it. And then we can simply run the optimization. And what we'll see here is the GUI will be running the optimization. We'll speed it up a bit, but you can see the design region updating and the fields updating as the optimization runs. So you can kind of monitor things. And you can also monitor like the objective function and the penalties and those things on a separate graph. So the design region is optimizing. You can see the progress of the optimization. And then when it's done, you can visualize the final results. So you can see the field intensity pattern. You can get an overlay with a structure. And then you can inspect the design region. And you can even export the design region to a GDS file if you'd like to fabricate this device. Or you can export it to another Tidy3D simulation if you wanted to do more studies or if you want to do more optimization. So again, the Python version has been released for some time, and this graphical user interface will be ready in a couple of weeks. We're just in the final testing. So I think with that, it'll be very easy to set up inverse design problems. And I think basically anyone can do it. If you've already set up the simulation, it's very straightforward to convert it to an inverse design. But the main focus of my talk is really how powerful and flexible Tidy3D inverse design is, and how we can go far beyond this sort of framework for defining inverse design problems. So this is, in my opinion, where things get really interesting. So as I mentioned, Tidy3D simulations are all differentiable, and we have a functional approach to defining inverse design problems if you wish. The idea is as follows. So let's say instead of just a high-level interface, I want to just write a function to define my design region. So it's just a function of my in Python that takes my optimization parameters and returns a structure that I want to inject into the simulation. So in Tidy3D, you can write code like this. You can also do custom parameterization. So you can say how your parameters transform, let's say, to the permittivity values at each pixel. You can do custom penalties, so how you want to penalize various combinations of parameters. And you can do custom post-processing operations. And you can combine all these together to do extremely flexible and general inverse design. As long as these functions are differentiable, so they just involve some kind of differentiable operations, you can just write your own custom code and do inverse design exactly the way you want. So let's just take a complex problem just to show you just an example of just kind of to show off what you can do with this interface. So let's say we're doing a gradient coupler optimization. We can specify, in this case, maybe a broadband mode power. So we're going to sum the power over a frequency spectrum. We're going to insert a permittivity grid here that we're going to optimize with topology optimization. We'll add a custom fabrication violation constraint that we just are implementing and maybe testing out. And we can also add things like take the taper here and discretize it using, represent it as a polygon, where we're going to actually modify the vertices of each of the points here independently as part of our optimization. We're going to also fit a spline to each of the 3 adjacent points in this curve, and then compute the radius of curvature and like analytically, and minimize some penalty over that radius of curvature calculation. And for good measure, we're going to compute the pointing flux on this plane and then minimize the flux that gets scattered from the simulation. You can define all of these with your own custom functions and put them all together and optimize. And you can see, in this case, we've done this again, 3D. You can see we've done a topology optimization of the coupling region. And at the same time, we've created this kind of curved taper. And you can see that the device is coupling efficiently into the waveguide. So this is just a preview of like what I'll talk about the rest of the talk, and just to show you the flexibility and the power of this approach. So now I'm going to talk about exactly what is the design of our tool and why we've designed it that way, and then how we've made this all work. So I need to first talk a little bit about software design and basically how would you, if you were starting from scratch and from first principles, how would you set up the ideal inverse design tool to kind of motivate the way we've done it? So first, I'll kind of breeze through how, what components do you need for an inverse design tool? Of course, we need some solver to solve the equations. We need a programming interface that basically, allows you to talk to the solver and specify what you want to simulate. The crucial thing is we need a figure of merit definition. So we need some way to define the problem we want to optimize for inverse design. And finally, we need an optimizer that kind of does the heavy lifting and actually figures out the right parameters for us. So we talked a lot about the solver. We have a massively parallel GPU, cloud-based FDTD solver. It allows fast and large-scale 3D problems. I recommend you check out our other examples if you want some more information on that. I'll kind of gloss over this. We can just assume it's a black box for the rest of this talk. We've also built a really nice Python interface to Tidy3D, and I think this differentiates us from some of the other commercial tools for FDTD. So we have a Python package that's open source. It leverages Pydantic which is basically a way to be very explicit about these different components like structures, geometries, monitors, and the simulation. They're all defined basically as data classes with very well-defined parameters. they can be exported to our servers with just a very thin web API wrapper. And then we can get the data sets back. In this case, we use Xarray to do multidimensional labeled data sets for you to get your simulation measurables. And all the front end interfaces really easily with other tools such as SciPy, PyTorch, and other Python tools. Now, the crucial thing is the figure of merit definition. And this is really how you tell your computer what you care about and what you want to optimize. Mathematically, this is a function that takes n parameters and returns one float, which is a figure of merit. And canonically, what you would do is you have your design parameters, which are maybe just some kind of abstract, like an array of values. These will kind of define your simulation. So given your parameters, you can create a simulation. You can run that simulation with FDTD to get a data set. And then from the data set, you can extract your figure of merit. So this is the kind of typical pipeline. And this is what we want to basically model with our inverse design tool. And finally, the optimizer, again, we need an optimizer. It does the work for taking the initial device, computing the figure of merit, figuring out whether the figure of merit is good enough. And if not, it uses the gradient of the figure of merit with respect to the parameters to update the parameters. And it just keeps repeating this process until you get a final device. There are a lot of very good optimizers out there that are open source, and we decided not to try to implement our own, and instead you can use one of these, and it works perfectly fine because our tool integrates so easily with these. So we'll kind of ignore this part as well for the rest of the talk. So let's focus on the figure of merit. How do we define a figure of merit in a way that's both easy to use and flexible? So let's take an example, again, the grading coupler example, except this time we're going to, instead of doing topology optimization, we're going to do something we can do in TidyGrad, which is we have some grading teeth, and we're just going to independently vary the width of each of these grading teeth. So those will be our parameters. Let's talk about how you could set this design parameterization up first. So how you define the grading coupler as a function of your parameters. Again, we need to define this mapping. So basically, it's a mapping from our design parameters to the tooth width, and then to the structure that we're simulating, right? The simulation. So how can we define this in code? Well, one way is the first way I showed, which is just, you ask the developers to create some grading coupler class, you tell it how many teeth, where they are located, and then this is defined by the developers, and implicitly in the background, there's some mapping then from the parameters to the structure, but you have no control over it. So it's easy to use, but it's quite limiting. Now, the functional approach is kind of like this. Basically, it's a little more code, but you have a function now, coupler, that takes parameters and it returns a list of structures. And your job is to implement this function. You just say for every parameter, compute the tooth size, and then create a TidyGrad structure and add it to the list. So these are both equivalent ways of doing things in TidyGrad. The first is easy to use. The second is essentially extremely customizable. Okay, let's talk about metrics, the other kind of crucial component, the objective function value. So in this case, we want to define this mapping. We have a simulation data set, some field pattern, let's say. We want to compute the mode amplitudes, and then we want to kind of extract the figure of merit, like absolute value squared, let's say. Again, one way is to require the developers to implement a coupling efficiency class at a high level, which is quite easy to use, but it's, again, limiting. What if you want to do something more complicated? Another way is just create a Python function, figure of merit over your data set, and it just extracts the data, it extracts the mode amplitudes, takes absolute value squared. Again, in TidyGrad, you could do both of these, and they each have their own pros and cons. So in general, our approach is this. We have our cloud-based FDTD solver. We have tools for automatic differentiation. We've written TidyGrad so that this whole process of parameter to structure to simulation to data to objective is differentiable and sort of defined with these functions if you wish, and it just wraps these kind of low-level tools. And then we have this higher-level plugin, which we call the InvDes plugin, which provides kind of high-level interfaces that wrap this lower-level TidyGrad code to let you kind of do things at a higher level. And then we have a graphical user interface, which in some sense mirrors this inverse design plugin. So it all fits really nicely together, and there's a clear hierarchy here. And but it's all kind of enabled by this lower level functional approach. Okay, so now I want to talk even more detail about how this functional approach works, how we made it work, and then give you a little just kind of tutorial or introduction to automatic differentiation if you're not familiar with that already, because a lot of these tools are essentially built upon this. So the figure of merit I was showing is a very simple pipeline. It can actually be very complicated, depending on your problem. You can probably already imagine some scenarios that you might want to do that are more complicated than just simple one-to-one mappings. So as an example, let's say we had some design parameters. We want to create now like an ensemble of simulations with different parameters or different structures in them, run each of these, compute some figure of merit, and then add a penalty to the figure of merit for good measure. So how do you define it? How do you create an interface that can model this and then compute derivatives of this whole process? It looks extremely complicated. So that's what we're going to talk about here. We use automatic differentiation to do this. So I have to talk about the chain rule. I apologize in advance. But basically, just as a review, if we have two functions, f and g, this pipeline of, something passing into f and then passing to g looks kind of like this. And you can write this as function composition. So f of g of x. And what we want to know is, imagine f is our figure of merit. What is the derivative of f with respect to x? So with chain rule, basically we know that, df dx is just df dg times dg dx. So because we know f and g, they're both simple functions, we can plug in their derivatives and we can get an expression for df dx. The key point here is that if you have function composition, which is sort of like this pipeline, then you're multiplying the derivatives of each of the steps in the pipeline. So that's kind of the underlying basis for this. Now it turns out, how do you do this for more complicated, and how do you generalize it to more complicated functions? So let's say we had a function like this, which we can write mathematically or in code. You can see that we can represent this function as a graph. We could call this a computational graph, where we send in x, we have these nodes that define operations like sine, cosine, addition. And when we want to compute f of x, we just send an x in and then we let it propagate along this graph, and then we evaluate the output here. So it turns out if you want to compute the derivative of f with respect to x on this graph, the way you do it is by using the generalized chain rule. What you do is you construct this backwards propagating graph. So you reverse all the arrows, and then for the nodes, you replace the operations with their derivatives. So sine of x becomes cosine of x, for example. And then you just propagate information backwards through this graph. Of course, the output df df is just 1. So you start with 1, and then you send 1 in, and you can see that we start to multiply 1 and all of the expressions by the derivatives in this graph, and we build up an expression. So we take all of the paths from output to input, and we sum them up, and we can get some expression that's, the derivative, and you can verify that this works. So what do we need to define then this computational graph, this back propagation? So a little bit of a technical detail, but if I have some node here, what I want to define is not so much the derivative of f of x, but actually what's known as the vector Jacobian product. And that's really, if I take the Jacobian of f, and I have let's say this is a multi-dimensional function. So I have some vector v that's kind of containing my error signal or my derivative signal from downstream in the graph. And what I want to compute is what is the Jacobian times this vector v. So that's why it's Jacobian vector Jacobian product. And we don't do this with an explicit Jacobian in automatic differentiation because that could be quite large and cumbersome. In fact, this is just a function of v that returns the operation of df dx on v. So it's a bit of a technical detail here, but this is how it's done, and it will become important later. So in practice, what AD tools let you do, or automatic differentiation tools let you do, is apply the automatic, the chain rule for a computational graph automatically in your Python code. So if I write my Python function here, f of x, I can evaluate f of x, which in some sense is like running the forward graph. I can use a tool like AutoGrad, which is a AD tool, to say, give me the gradient function of f. So it takes a function f, it returns another function, grad f. And essentially, if you wave your hands, what this is doing in the background is building this reverse network here. And then if I call grad f on my input, it then evaluates the derivative. So it actually plugs everything in. And What's really neat about this is as long as AutoGrad knows about addition, cosine, sine, everything else, it can handle arbitrary complex code automatically. And there's no derivatives needed. You don't need to derive anything by hand. And tools like AutoGrad pretty much cover the entire NumPy library, so you can pretty safely use most NumPy functions in your code, and they'll just work without any extra effort. Of course, you can define your own, and we've defined a few for convenience in Tidy3D. So this is really powerful. And as was alluded to before, you can see why this would really enable a lot of modern day, especially deep learning and AI. So you have tools like PyTorch, which is very popular, probably the most popular AD tool out there, where you can write these extremely complicated machine learning models that do all these operations, and they have billions of parameters. All you need to do is write the operation, the forward to f of x in PyTorch. And then if you want to train the model, which involves computing gradients and doing gradient descent, you can just ask PyTorch to get the gradient, and it just works. There's no derivatives needed. I think if we had to do manual computing of derivatives, like people would stick to very simple models, and probably we wouldn't see all the progress we see today. So this is really like a key component, along with the hardware, for training large-scale AI models. But it also can be used for inverse design. It's pretty much, I think these two problems like map to each other very well. They just have different names. Inverse design, again, you could think of it as like training a neural network or a machine learning model, except your weights or your parameters are kind of the structure that you're getting at the end. So how does this work for inverse design? How do we kind of make sense of this? So in our figure of merit function, in inverse design, you can imagine we have some nodes that are just setting up the function or post-processing, but we also have a node that's running the simulation. So for example, it takes a simulation and then it runs it over our server and gets the data back. So of course, AutoGrad's not going to know about FDTD or Tidy3D or anything. So our job is really, how do we tell AutoGrad or PyTorch or whoever, what is the VJP of the simulation run, the FDTD run? And if we can plug that in to AutoGrad and register with AutoGrad, then it enables you to write code like this, where you just have any function, f of x, something sets up the simulation. Okay, if it's AutoGrad compatible, it works. You then run the FDTD simulation on our server, you get some data set, and then you get the figure of merit of your data set. And again, as long as we tell AutoGrad about the second line, how to handle the derivatives, then we can just ask AutoGrad for the gradient of this whole thing, and it will work seamlessly. So that's in fact what we've built. Now I need to get to go one layer deeper into how we compute that VJP. And this is the final final layer. But basically, the way we do it is through adjoint variable method. So adjoint variable method is the way we compute gradients of essentially, we could say simulation code. And as an example, we can look at a linear system. So maybe FDTD, you can express it as a linear system. So in the linear system, we have AX equals B, and we're solving for X. So A is the sister matrix. It contains, let's say, your device and all of the boundary conditions and information about your setup. X is the solution, so the field solution, E and H fields, and B is the source, so how you're exciting your system. We can assume that our system depends on our parameters, P. So, changing some value P changes the width of a waveguide or something like that. And we also can assume that the figure of merit depends on just the output. So, of course, it can depend on P, but for sake of simplicity, let's say it just depends on the solution, the electric fields that you measure. What we want to compute for our training is the FDP. So we need to kind of like plug in the derivatives, and we will get an expression for DFDP if we just use linear algebra and calculus and plug it in. So let's go through these each line by line. So we have the matrix DADP. So that's how the system matrix changes with parameter P, which is actually quite straightforward generally. We have our original solution here. And then this is the key term. So we notice there's an A inverse. So what we can do is we can say, well, everything here is just the solution to a new linear system, which we call the adjoint system. And this adjoint system now has a source that depends on F. And specifically, it's minus df dx. So this figure of merit now gets converted into a source that we use for our new adjoint system. And then once we've solved for x tilde and x, we can just do this overlap integral, essentially. So or this inner product with dA/dP. Now, the real secret here, or the whole thing that makes this all work, is that you notice that x tilde and x, they don't depend on p. So basically, if we have 1,000,000 p or 1 p or 2 p, we just have to solve x tilde and x once, and then we have to perform this overlap integral for all p. But it's very cheap, typically, to compute. So effectively, this gradient is computed with just 2 simulations. There is a separate post-processing step, but yeah, just 2 simulations. These simulations are, of course, the real limiting factor. And this is really what enables all of this to work, because when we're doing inverse design, you'll have hundreds of thousands or millions of parameters. So you wouldn't want to be doing hundreds of thousands of simulations, of course. Okay, so more intuitively, how does this look? So of course, for the waveguide bend, we have this as our forward, our original simulation. Now, remember, in that waveguide bend, we're measuring at the bottom port. So df/dx is going to be defined where we're measuring, and we're going to be injecting a mode that sort of depends on the figure of merit. So it looks like this. And then the overlap in this case, since we're doing topology optimization, basically we're just going to multiply these 2 fields together in the design region and then sum the result over each pixel. And that turns out to just give you the gradient of your figure of merit with respect to the permittivity of each pixel. So this is the typical step, 3 steps for adjoint. So finally, how do we take this information and the automatic differentiation and synthesize it together? So how do we plug adjoint into automatic differentiation? So again, we have to define the VJP. So this is the steps that we do. So of course, you define your figure of merit function. It takes parameters. It sets up the simulation. It runs the simulation. You get the data, and it returns a figure of merit, which you pass. Okay, AutoGrad handles the figure of merit. Now, when you ask AutoGrad for the gradient of this function, oh, of course, I forgot to mention, we also will store the fields that we need to compute gradients. So for example, in the design region, even if you don't specify that, we'll just do that automatically. So now we ask AutoGrad for the gradient of this process. It says, okay, here's your vector v, which contains the df/dx part. We take that, we interpret that as, we convert that basically to adjoint sources. So there's a well-defined mapping from, let's say, data set values to adjoint sources. So we set up this adjoint simulation and run that, and again, store the fields in the design region. Well, now we have everything we need. We just, for every parameter, we compute the df/dp that we need using some overlap integrals, and we just package everything into the proper data format that AutoGrad needs, and then AutoGrad's happy, and it gives us our gradient back. So this is kind of how we've done it. In practice, it doesn't look, you don't have to know anything about this process, but all you need to know is that this is what's happening in the background, and you'll get gradients automatically, and it will run a separate simulation in the background. Of course, it's extremely complicated for all the edge cases that you have to handle, and then there's all these technical details. But again, we've done all the hard work. You don't have to think about it when you're using the tool. So just to recap, again, what is this, like, why have we done this? What does it give you? I think the main reason is it gives you unlimited flexibility to be creative with your work. So if you thought about a new parameterization or a new figure of merit or a penalty function or something you want to try out, it's very easy to just write your own code, plug it in, and test it out. So your code kind of becomes essential in the whole pipeline, and we can just handle it without any thought. It's also more of a technical, developer note, but it's very straightforward for us to just add new features. So for example, because it's so general, we want to support a new parameter like a sphere radius. We just have to define how this inner product looks under a parameter p, where p is the sphere radius. And so that's all we need to implement. There's not a lot of boilerplate. And then it's also for data, if we want to support a new data structure output, we just need to define how that data transforms to an adjoint source. So it's quite straightforward. And as a result, we've just been on kind of a speed run to implement all these features that you might need for inverse design. And we have pretty much, we have quite a lot of features. This is not a comprehensive list. And we have again, TidyGrad has an open source front end. If you want more features, it's actually quite useful for you to bug us on the open source, and front end, just let us know you would like something, because that will bump it in priority. But we do support a lot of features. And I'd like to show off some of those features now, and then we'll kind of wrap up with a Q&A. So let me just show a few examples to just get the kind of discussion started and show you some things we've done recently with inverse design. The first is, we've done wavelength division demultiplexing problems. So these are, somewhat straightforward topology optimization problems. But what makes them interesting is that they have these complex broadband objectives. So we want to look at the power of these channels, and we have multiple simulations going on in these optimizations. So you can check out this notebook where we've done, WDM. We can also very easily do multiple co-optimized design regions. So for example, we've done a bilayer grading coupler where we have a silicon nitride layer on top that's being topology optimized, and then a silicon layer below that's being topology optimized at the same time. So, we're running our simulation, and it's just basically if you just define two functions for each, define a function for each of these and add them to your simulation, it works right off the bat. So that's quite nice, and I'll talk a little bit more about that later. We could also be able to do things that are pretty powerful, like for example, most topology optimization or this pixel by pixel optimization just works on the linear kind of relative permittivity, but we can do more powerful things. So in this case, we can do metal topology optimization. So we basically have a grid where each pixel can vary between air and, in this case, gold. And this is gold measured from experimental data and fit to a dispersion model. And what we can do is we can compute gradients with respect to the coefficients in the dispersion model. And so then we can linearly interpolate between air and gold. So it's kind of complicated, but basically it works. And you can define these, antenna optimization problems quite straightforwardly. Now, I think an underappreciated and maybe underutilized thing is shape optimization. So rather than doing these pixel by pixel approaches, I think it's often a really good idea, if you can, to just define things in terms of geometric parameters. So with Tidy3D, we have these polyslab objects, which let you define some basically extruded polygons. And we can set up polygons and compute gradients with respect to shifting any of the vertices in that polygon. So you can imagine you can set up these waveguide bends or tapers and let them evolve and let their edges move around. And you can let them move around kind of freeform, or you can parameterize them so they move in a very specific way, like on a specific trajectory or parameterization. And this is really powerful. And yeah, I think one other thing is we've included a minimum radius of curvature penalty. Like we have all these convenience functions that you can import. One of them is a radius of curvature penalty. And what it does is it's just to show you the power, it will fit splines to these polygons. And based on, you can compute analytically the radius of curvature at each point on the spline. And then you can feed that to a penalty function. And then you can minimize like the amount that each vertex or each three vertices go below this minimum radius of curvature. And all this is handled by TidyGrad, so you don't have to worry about it. And yeah, so it's quite powerful. You can get, if you didn't apply that, you would actually, from experience, you would get extremely jagged structures. So it's kind of essential for these optimizations. Another analog of that is just direct geometric primitive optimization. So, we have these other objects like boxes, which are just rectangular prisms or cylinders. What you can do in Tidy3D is just say, I want to set all my boxes up in the simulation, and then I'm going to move the boxes around, either the centers, or I'm going to change the size of the boxes. And this will just work again with AutoGrad and with Adjoint. So we've done meta lens with both changing a box and the cylinder radius. And again, you can shift. We've done grading coupler optimizations where you've shifted the grading teeth around. So you can just start it off with the kind of nominal device that you think will be the best, and then you can just let it optimize from there and see where the grading teeth move around with constraints or with whatever parameterization you want. So that's quite powerful, and often where I would recommend you start if you're getting into this, actually. Final couple things, we have a lot of very kind of complicated field operations you can do and take derivatives of. So just to show that off again, we've did a meta surface optimization where we just took our logo and said, we want to compute the intensity above the metasurface, and then we want the intensity to look like our logo. I think it did it as well as it could. Maybe there's some diffraction limit problems going on here, but it did a pretty good job. But it was just to kind of show off and just show how flexible this is. You don't have to wait for a developer to define this problem for you. You can just specify it and go. And we also, of course, support field projection. So you can optimize a grading coupler to, in this case, compute the angular power in the far field and then maximize the one wavelength for one angle and one wavelength for another. And that works. Just so you know, this is in preparation because this is not released yet, but it will be released in our next minor release in a couple weeks. And then the final thing that I want to highlight is we also, I mentioned single simulations. We can also do the same approach with multiple batches of simulations. So, or I should say batches of simulations. So if you define some problem, let's say where your objective function is not just looking at a single simulation's performance, but actually create an ensemble where some simulations are smaller or eroded, some are larger, and you're kind of trying to capture some fabrication variance or something. And then you want to compute the objective for each and then take the worst one as your actual figure of merit. We can easily handle problems like that. And the batch itself is differentiable. So each of them will run in parallel and we just figure out how to stitch all the derivatives together at the end. So these kind of problems are very straightforward with our interface. And the final thing to show off something similar is, we have been able to do co-optimizations of different structures where I have a circuit simulator that's, in this case, something called SAX, which is compatible with a platform called JAX. And what I have are two different Tidy3D simulations where I compute the scattering matrix of each one. I tell SAX what the scattering matrix is, and I also give SAX a circuit level objective. So for example, when the phase of my phase shifter is 0, I want to output to one port, and when it's pi, I want to output to the other port. And we can co-optimize these simulations, each contained in their own simulations, running in parallel, and all kind of chained together in this circuit simulator. And really the only reason we're able to do that is because of this generality. Okay, I think I've talked enough. Thank you for listening. If you have more, we're going to do a Q&A, so feel free to ask me questions. And we'll also do a quick little demo of the topology optimization bend, and then also the graphical user interface. But in the meantime, if you want more information, we have probably hundreds of Python examples in our documentation. So you can check that out. And we have maybe a dozen or two inverse design examples as well. And all of those have code, Jupyter notebooks you can download and run as is. They work right off the bat. And then we also have a series of inverse design lectures with Professor Fan, where we've just kind of created videos and code and slides to explain the fundamentals of inverse design, things I didn't go into, like details about the Adjoint method, details about parameterizations, kind of practical tricks and tips. So I really recommend you check that out, especially if you're a beginner. But yeah, again, thank you so much for listening. I will, I guess at this point, I'll take some questions.